Hello, and thanks for watching. The purpose of today's video is to develop an understanding of calculus, particularly differential calculus, in this thing called a derivative. But before we can understand a derivative, we've got to go back a little bit and explore some stuff we might have learned prior to calculus. So to set everything up, I want to point out that we've got this shape, this trapezoid, and the things that are the same, these two sides will always be 60 centimeters, and the top base will always be 100 centimeters. What's going to change is the length of the bottom base. By extending this side and this side out by the same amount, we continue to get a regular trapezoid, but the shape is going to change. And as a result, whenever the shape changes, if I make x bigger, it's going to be a shorter trapezoid. It's going to have a different area. So this function right here will tell me the area of the trapezoid depending on which values I choose for the base x. So, in algebra, we might have, advanced algebra, we might have actually seen how to calculate average rates of change. And just to jump ahead, you can see, for example, here, the value of x starts at 24 and it goes up to 34. So I'm increasing x by 10, therefore increasing the base by 20. And I'm interested in how the area changes. Now notice a of 24 shows 6,819, a of 34 shows 6,625. There's not a significant change in the areas, although the area has dropped a little bit. Now that's referenced over here by this particular graph. This line right here, this purple line, is called a secant line. It connects the 2 points, that is the area at 24 centimeters and the area at 34 centimeters. If I calculate the slope of that purple line, I have found what we call the average rate of change, and in this case it'll be the average rate of change in the area of the trapezoid. So, by finding the change in y, that is the difference between these two areas, and dividing that by the change in x, which is 10 centimeters, we can calculate the change in area per centimeter increase. And what this says here, negative 19.43, is that for every centimeter from 24 centimeters to 34 centimeters, the area of the trapezoid loses about, or drops by about 19 square centimeters. So that's why it says negative 19.43 square centimeters per centimeter. Well, that's fine. That's advanced algebra, algebra 2 kind of stuff. But what's it for? Well, just to drive this point home just a little bit further, I point out that if I was to change from x equals 44 to x equals 54, it's still the same change in x. That's still 10 centimeters more in x. But what I observe here is there's a significantly greater change in area, a reduction in area. Before, I had 10 centimeters change in x and only 19 square centimeters per centimeter increase was lost in area. But later on, when I still change x by 10, there's 184.6 square centimeters per centimeter lost. And so for every one of the 10 centimeters from 44 to 54, we're losing an average of 184.6 square centimeters. That again is evidenced by the slope of this purple line called the secant line. So here we can see that the slope of the line is not very steep, and therefore we have a small decrease in area, and here we see the slope of the secant line is much steeper, corresponding to a greater decrease in area. Again, so what, and what does this have to do with calculus? Just want to point out one more thing. Another drop, this time x only went up by 5, but we see a significantly greater loss in area, and now it's up to 458.6 square centimeters lost for every centimeter increase. And that also corresponds to a significantly steeper secant line. So what we learn is that the steepness of secant lines corresponds to the speed or rate of change of any function that we study. Again, what does this have to do with calculus? Well, you see, you can find the speed of an object really, really close to its at any point, but let me back up. What I have here is not the speed at which the area is changing at x equals 44, and this number right here is also not the speed at which the area is changing when x equals 54. At 44, the area is decreasing a little slower than at 54, where the area is increasing a little faster. So what the secant line's slope tells me is not exactly how fast the area was changing at any moment, but rather on average how much was the area changing over that specific space, or interval it's called. If I want to know how fast the area is dropping when x is 53.5, I could get an approximation by making another value very, very close to x. So if these two numbers are really close to each other, I can get a secant line that gives me a very accurate area calculation. In this case, it's negative 276.7. So that is an estimate of the speed at which the object's area is decreasing. However, if I tried to calculate the slope of a line when the change in x is 0, non-existent, that is to say A is 53.5 and B is 53.5, there is a 0 change in x, which gives me an undefined slope. So there's a slope here, clearly. In fact, I know that there's some sort of rate of decrease in the area of the trapezoid near x equals 53.5. But when I tried to actually calculate it, I couldn't, because I was required to divide by 0, and since we can't divide by 0, I can't find the exact speed at which I'm changing. So once again, average rate of change can get me to get a pretty good estimate, but it doesn't tell me exactly how fast we're going. So this is where calculus comes from. So that is an introduction to the problem, and that greater minds than yours or mine had solved a couple hundred years ago. So just to restate the problem, I understand average rate of change, but what if I want to find instantaneous rate of change? My rate of change algorithm falls apart, and it won't tell me how fast I'm going at a specific time. So that's part one of this video. It's just setting up the problem. What is the problem? We're trying to find out exactly how fast we're going at a moment in time, when all we know how to do is find out on average how far we're going in an interval of time. So in the next video, we'll talk about how this problem is solved and what we do with that information. Thanks for watching.